Good afternoon, folks. How are you today? We are in week number 11. So today, Wednesday, we are having this lecture. We'll come to a new topic in a moment. So this is lecture 31. And then Friday, we are going to have a review for test 2. And then Monday, we are going to have the test. So as you see on this slide, test number 2 is on Monday, November 2nd. It is synchronous, so make yourself available. Sign into my courses 3:35 to 4:25. I'll set the quiz to be from 3:30 to 4:30, just to kind of cover up time. So online, synchronous, same as test number 1, 36 multiple choice questions similar to quizzes. And I said we are going to have a review this Friday. It'll be online, synchronous. We are going to use Zoom, so sign into Zoom. I've sent you a link Friday, which is October 30th. Okay, so let's see what we have done so far. So I gave this review. We learned how to solve root of a function or one equation in one unknown. Then we also learned how to integrate a function. And we learned how to differentiate a function. And we can get derivative of any order. Now what we are going to do is we are going to learn how to solve a differential equation, an ordinary differential equation. So obviously equation means something is equal to something. Differential means these equation involves derivatives of some kind. And let's see, what do we mean by ordinary? Ordinary versus what? Ordinary versus partial. So there are ordinary differential equations and there are partial differential equations. So if you have not taken a differential equations course as yet, do not worry about it. You are going to be properly prepared for taking that course. If you are taking it simultaneously, I hope whatever I am talking about this week and next week would be very useful to you. And if you have already taken a differential equation course, I hope you learned some new insights from my description. So ordinary differential equation versus a partial differential equation. So ordinary means that we have one independent variable. So we are going to take derivative with respect to that independent variable. So usually this independent variable is either a dimension like x or it is time usually, but not always. And of course, if we have only one differential equation, we'll have only one unknown or what we call one dependent variable. So we are going to choose x usually, and for dependent variable, we are going to choose y. Partial means we have more than one independent variable. So now we can take derivative with respect to each. So that's why we will have partial derivatives. Okay. So we write our one ordinary differential equation. And we write it in this form. dy dx is a function of xy. So we know x, we know function, we want to find y. That's our goal. Usually, in order to solve this equation, we need one condition. So we need to know y at some x value. So we say y at some x0 is y0. So we know this. So we know x0, we know y0. And what we want to find is therefore what is y at the next value, x1, x2, x3, so on and so forth to xn. So the question is, if you already took differential equations, you learned methods to solve a differential equation. Why do we want to learn numerical methods? Because the methods that you have learned in differential equations are mostly for linear functions. So the f function may be nonlinear in y, and many of those methods may not work. Second, the function may be embedded in hardware or software, so we may not know function exactly. All we do is we feed x and y to a black box and it gives us the function value. So we may not know function explicitly. Or function may be a complicated function of x and y that you may not want to integrate. So in this course, what we will be able to do is we will be able to solve any order ordinary differential equation. So m order ordinary differential equation. And we'll find out that we will solve them by first transforming them into m first order equations. So suppose m is equal to 3. So we have one third order equation. And I'll define order in a moment. But what we can do is we can write this into 3 first order ODEs. So what we will do is we'll begin to learn how to solve one first order differential equation. Then we'll learn how to solve two, which we can generalize to two or more. So I just said ordinary implies that we have one independent variable, usually x or t. We are going to choose x. Order of an ODE is same as the order of the highest derivative in the equation. So if you look at this equation, we have a third order derivative, we have a first order derivative. This is like zero order, so that is just y alone. So in this equation, the highest order derivative is this one. So we have a third order ordinary differential equation. Then degree refers to the power of the highest derivative in the equation. So if you look at the equation below, we have a first order derivative, first order derivative. So this is a first order differential equation. And this first order derivative is squared. So its degree is 2. So the power is degree and highest derivative is the order. So the equation above that we had here, the power was to the 1. So third order, first degree equation. This is first order, second degree equation. Okay, so in this course, we are always going to consider first degree differential equations. Because if degree is not 1, we can always take root of the other side. So we'll always choose differential equation of degree 1. So now let's see what is linear versus non-linear ODE. So let's consider dy dx is given as a function of xy. So the question is dy dx linear with respect to this unknown or not? Let's suppose if it is, then we can separate it. We can say it is something times y, and that something we call could be a function of x, and the remainder could be some other function of x. So this is a linear differential equation. Let's take another example. When we write second order differential equation, we put everything on the other side, which can involve x, can involve y, can involve dy dx, which we'll write as y prime. Now, if we have a linear, so this is second order. So if this was linear, then second order derivative would be linear in y and linear in y prime. So what we'll do is we can separate it out. We can say something times y prime plus something times y plus whatever is the remainder could be a function of x. So this is now a linear second order ODE. So same way you can see, suppose we want to write two first order ODEs. So two first order means we have two unknowns. So we have unknowns y and z. So first we'll write dz dx is a function of x, y, and z. If it was to be a linear differential equation, same thing, we'll have something times y plus something times z plus remainder. And these could all be functions of x. Similarly, we could have another differential equation. Of course, it is going to be a different function. If it was to be linear, then we'll have these coefficients which are functions of x of y, z, and remainder. So this is how you can recognize what order, what degree an ordinary differential equation is, and how many dependent variables there are. Okay, so we are going to start with a one first order ODE. So we are given that dy dx is a function of x and y. So could be nonlinear. So we are going to solve all kinds of first order ordinary differential equations. So when we say we are given, it means that we know the function and we know the x values. We are also know one initial condition. So we know at some x0 what is y0. And then what we want to find is y1, y2, y3, so on and so forth, up to yn. And let's say our x's are equispaced. So let's look at it graphically. What we want is, here is x, here is y, and let's say x versus y curve looks something like this. So at some x0, we know this y0. And then we have equispaced x's, x1, x2, x3, and we want to find these values, y1, y2, y3, so on. Okay, so that is our problem statement, and we are going to cover three methods to solve this one first order ordinary differential equation. First, we are going to cover Euler's method today, which is an explicit method. Then we are going to cover an iterative Hume's method. Iterative methods are implicit methods. And then we are going to cover Runge-Kutta fourth order method, which is an explicit method. Before I move on, I just want to remind you that I am not teaching you differential equations analytical techniques. So on the quiz, you may find a problem such as saying, given this differential equation, which of the following is the solution? So I don't want you to solve, but basically what you have is you have a problem and you found a solution. Of course, in DiffyQ, you would have learned analytical techniques. Here you are learning numerical techniques. So what you need to do is you need to verify or validate that indeed it is solution to your particular problem, and that you can do by substituting the unknown in your problem and see if it satisfies the problem. Okay. All right. So let's see, what does a solution mean? So we say we are given dy dx is a function of xy. So what we can do is we can write it dy is fxy times dx. We can integrate both sides. At xi, we know yi. Let's say at xi plus 1, we want to find yi plus 1. So our yi plus 1, when we integrate it, left hand side would be this, and right hand side would be this integral. So let's see what this means graphically. So here is x, and here is our dy dx, which is a function of xy. Underneath it, I'm going to draw y, and at xi, we know yi. Let's say y curve looks like this. So we know yi. And let's say our this curve looks like this. Okay. So what we want is at xi plus 1, we want this yi plus 1. So what this equation is telling us, that this difference, which is this height is the area, this integral, which represents therefore the area under this function curve between xi and xi plus 1. So area of this strip, that's what this height is. So all we are doing is we are estimating this area by different methods, approximating it. That's what numerical method is doing. So why is it different? Previously, it was just a function of x. So we could estimate the area here. We could evaluate the function here. Now, since we don't know yi plus 1, we don't know this function value. So we need to approximate this strip area. So what does Euler's method do? Euler's method says we are going to estimate the area of this strip by building a rectangle. So Euler's method says that this area is this width h times the height, which would be the function at xi, yi, right? So at xi, yi, this is function at xi, yi. So Euler's method says yi plus 1 is yi plus h times function at xi, yi. Okay. Let's do an example. And please do it along with me. Pick up your calculator. So let's suppose we are given that our y prime dy dx, which is a function of xy, is a function square root of x plus square root of y. And y at x is equal to 0 is equal to 1. So that's our initial condition. We are told to use h of 0.1. So we make a table. So at x is equal to 0, y is 1. In our table, we are going to space x 0.1 apart. Okay, so we are going to evaluate the function, and then we are going to multiply it by h. So we evaluate square root of 0 plus square root of 1 is 1 times 0.1. So we are going to add to yi this area. This is our rectangular area, so we'll get 1.1. So now we need a calculator. So we'll do square root of 0.1 plus square root of 1.1 is 1.3650. We'll keep 4 digits. So we'll get 0.1365. So we will add it to 1.1. So we'll get 1.23650. So we do square root of 0.2 plus square root of 1.2365. So we'll get 1.5592. That'll become 0.15592. We add it to 1.23650. We'll get 1.39242. So again, do square root of 0.3 plus square root of 1.39242 and carry on the calculations and see if you match my rest of the table. Okay. All right. So let's see what about our truncation error here. So when we look at truncation error, we can derive it very simply from Taylor series. So from Taylor series, what do we know? yi plus 1 is yi plus h times yi prime. Remember that was dy dx plus h square by 2 second derivative, and let's chop the series here. So this is our Euler's method approximation. and this is our truncation error. What is zeta? Zeta is somewhere on the strip. We don't know where. So we just need to take the error bound. So what we are saying therefore is our local truncation error, which is one strip, is proportional to h square. So it's an order h square local method. But we should look at global truncation error. Global truncation error is n strips. So we'll multiply n times h square. Of course, n is proportional to 1 over h. So we will get global is order h. So Euler's method is considered order h method, global. Okay. So just as an example, here is our approximate solution to some problem as h is equal to 0.5, and here is our true solution. So you can see initially the error may be very, very small, but then it starts growing larger. But it can have any behavior depending on our differential equation. But we know something, that our truncation error is proportional to h in this particular case. So obviously, if we decrease h, we decrease the truncation error. But however, we will increase the round off error because we'll be doing more calculations. Because as h decreases, number of calculations or number of strip goes up. So remember, we had this discussion last time when we talked about Richardson extrapolation and Romberg integration. So we got to be careful here. If we use too thin a strip, we can increase round off error. So what we must do is, in order for us to check what kind of error it is, we should solve the differential equation using two different strip sizes and then perform Richardson extrapolation, just like you did in lab number 10. Okay, so let's stop here.